Okay, hello everyone. In continuation of our discussion about inductance and mutual inductance, we're going to take a closer look at the concept, and hopefully we get to a point that we can extend the concept of mutual inductance to an extreme and introduce a new component that is called transformer, and later on we're going to go back and take advantage of the devices that are called, or components that are called transformer in the next lectures. So we started by introducing the concept of inductance itself, and basically we explained that in an inductor the electrical energy associated with the movement of charge, which we defined a concept called current, which is charge that is passing through a cross section with respect, like in a unit of time. That energy associated with the charge is going to turn into a different form of energy, which is called the magnetic energy, and it gets conserved in that form. If you recall, with capacitors, something similar in terms of transformation of energy happened, in a sense that with the capacitor, once you start connecting that to a source of voltage, that voltage is going to cause charge to go through the capacitor, and as a result you get energy associated with, again, electrical domain, or charge that is being accumulated on the two plates into a potential energy or electrostatic energy, and that energy is conserved in the inductor. So that component, in other words, is an energy conserving component that conserves energy in the form of potential energy, and dual of that, in the case of an inductor, the energy turns into a magnetic field, and that energy is associated with the movement of the charge passing through the conductor. And so you can simplify this and kind of make sense of it by saying that the capacitor conserves energy in the form of potential energy, and the inductor conserves energy in the form of magnetic, which is a form of you could call kinetic energy, because it's associated with the movement of charge. So it's associated with the movement of something. So that said, how much of the electrical energy or energy of the moving charge is going to turn into magnetic energy and conserve in the form of magnetic field is really a function of how you form your conductor through which the current is passing. Now, we said by kind of looping the conductor around something, you intensify the magnetic field in the metal, and you can use the right-hand rule and kind of see how that happens. In other words, you make the magnetic field associated with each piece of this conductor to be condensed in a certain region, and because of that you increase the efficiency of the transformation of energy from the electric field to magnetic field, and therefore it reaches a point that you have to take that into account. Because normally even a piece of wire turns some of that electric energy, the current associated with the current that is passing through it, into a magnetic field. But normally that component of energy is small or negligible, and we don't consider just a piece of wire as a component that is transferring energy into a magnetic field normally. But once you turn it into this shape, then we reach a point that we no longer can ignore that component of energy. Therefore, there should be a correspondency between this inductance that is basically a measure of how efficient this component is in turning the energy from the electric domain to magnetic domain. We can relate that to the geometry of this component, the way that we are forming the inductor. And also, obviously, it has to have something to do with the medium in which the magnetic field is forming in. In other words, if this loop has some material in the middle that is other than air, you may then guess that the transformation of energy is going to be different, and in reality that is the case. The same way that in a capacitor, for example, whether or not you had air between the two plates or you put a dielectric component with the permittivity that is different than air or larger than air for that matter, the amount of energy that you get is going to be different. So for the higher permittivity, you get more of the electrical energy to transform into a potential electrostatic field, and that was shown by basically that shows up in the definition or the way that the capacitor is calculated when we know that the capacitance value is equal to the epsilon, the permittivity of the material that is in between, multiplied by the area divided by the distance between the two. So if this is d, the distance between the two. So A is the area of the plate and epsilon is the permittivity of the material that is in between, the dielectric that we put in between. So the same thing has to be true here. Now, we're not going to go through details of how this is true, but if you assume that the number of turns that you have here for this inductor is N1 for that matter, let's say this one is N2, then L1, assuming that there is no effect from L2 or for any other electrical conductor in the circuit on how the magnetic field forms in L1, you can prove that that's equal to N1 to the power of 2 times a constant called, times a variable called the permanence. And this permanence is basically a function of the material property of the medium, which is called permeability. And permeability is something, basically a dual of permittivity, but in magnetic domain. In other words, for the same amount of current that is passing through these, depending on what the permeability of the material or the medium is, you may get more or less magnetic field or more or less magnetic field density associated to the current that is passing through the wires. So let's repeat that. You can tune how much of the energy associated with the current that is passing through the conductor is going to turn into magnetic field and conserved in the form of magnetic energy by playing with the permeability of the medium in which that magnetic field is going to form. And that shows up in this equation by basically changing the value for the inductance. Now, the same way for L2, if you have a different number of turns for that one, that would be N1 and 2 to the power of 2 times the permeability of that inductor. And that's, again, with the assumption that these two are not going to have any effect on each other. So, with that in mind, we can clearly see that if we want a larger inductor, you can do two things. You can either increase the number of turns here and you get a larger inductance, and that's intuitive, or you can play with the permeability of the material by putting something here, specifically putting something, because we know that the largest density of the magnetic field is actually inside the loop, right? So if I want to intensify the magnetic field density or the magnetic flux density, then I can actually just simply change the medium within this loop, and with that the inductance is going to proportionally increase, which means I'm going to get more and more magnetic energy. So now, then we moved on and actually explain something else on top of that, and we said since magnetic field is just not for the magnetic field, we know that these loops exist that kind of all of them are concentrated in the middle, but they basically penetrate through the medium, and it's going to basically spread everywhere. And therefore, if you have more than one inductor in the circuit, it's quite probable that the magnetic field associated with one is going to affect the other. And therefore, we then defined this concept of mutual inductance, and therefore, when there was a current passing through one, and normally if there was no other one available, the voltage associated with the equation that relate the voltage to current would be only a function of the current that is passing through this one and the inductance associated with the component. But when we consider the effect of the other inductance on this one, then we had to actually use the concept of mutual inductance and take into account the current that is passing through the other one. And we wrote the equations and all that in the past few sessions. Now, the inductance value, M, you can write it as an equation like this. This is a coupling coefficient and is a number between 0 to 1. And there is this is a function of the permeance of this inductor and the mutual permeance between the two. And you can look up the book and read about this more, but at this point we really don't care about what exactly constitutes K, and only limit ourselves to knowing that the larger this number or the closer it is to 1, it means that more of the magnetic field that is formed as a result of current passing through one of these inductors is going to actually couple to, it's called a coupling coefficient, so it's going to couple to the other one. So at the two extremes, at the time that K equal to 0 on one extreme, that means that the mutual conductance is actually 0, which now at that point we don't have to consider the equation associated with mutual coupling, and each one of these inductors could be considered separately without, and the effect of the other one could be completely neglected on the other inductor. The other extreme, when K is equal to 1, it's exactly the opposite. It means that at that point, pretty much all, and we never reach 1, and we never really reach 0. But then if assuming that we're really close to 1, it means that all of the magnetic field or the magnetic flux that we have in 1 as a result of the current that is passing through it is going to couple and, in other words, pass through the other one, which is an extreme that is never going to happen, but there are ways to get close to it. So how do we do that? So first of all, to get more and more higher and higher magnetic flux density in the inductor, what we said is that we can actually put a material in the middle that is made of something that has high permeability. Okay? Keep in mind, permeability and permittivity are kind of dual of each other between electrical domain and magnetic domain. Okay, so if I do that, and if I do this for this one, then I can actually get closer and closer to a point that I can kind of neglect the magnetic flux that is anywhere else and only say most of the magnetic flux is confined within this material, because the permeability of this material is much higher than the permeability of air, and as a result, a lot of magnetic flux is in the material, whereas as soon as you go out, there's not much, right? Because the permeability of this material is so high, much higher than the air. What kind of material are those? Well, they're material that are called magnetic. Iron is one of them. Nickel, cobalt, and these materials are going to give you what we are just describing and get really close to a point that you can kind of neglect the magnetic field density or magnetic flux density that is outside that. Now, what you can do is to take this idea and make a loop here. In other words, take this material and turn it into a loop. Now, the magnetic field that is created in one is actually going to continue and go through the other one. And since we already said that if this permeability is large, I can ignore anything else that is outside, we kind of reach a limit at which I can say that all the magnetic flux density that I have here is going to pass through the other inductor. In other words, I'm getting really close to the regime where K could be considered really close to 1, at which point the mutual, so if K is really close to 1, then I can say M is really close to L1, L2, right? So if this is the case, something interesting is going to happen. At that limit, what I'm really saying is that almost all of the magnetic field is actually within this magnetic core, it's called, right? And there's a really good coupling between the magnetic flux in one and the other one. A lot of times you may not have something like this in a circuit. You don't want the electrical energy or the current and voltage in one inductor to affect the other one. But then in this case, we're actually going exactly for the opposite. And we really want to have this situation for a very specific reason. Because now what is going on is that the voltage and current of this inductor actually, in a way, is going to be completely coupled to the voltage and current of the other one without any real electrical connection. So these two wires, they're really electrically disconnected. They don't have to be connected. But the voltage and current that goes passing through are basically completely coupled. And if you write the equations, assuming whatever that I said so far, there's something interesting is going to happen. If I say this is the voltage V1 and the current is going in, and I say this is the voltage V2 and this is the current, the passing I2 that is passing through that one. With this assumption, I can prove, in this case, the current goes in, the voltage, current goes out, the voltage. I can prove that V2 over V1 is equal to N2 over N1, the number of turns of the inductor on one end divided by the number of turns for the inductor on the other side, and I2 over I1 is actually equal to N1 over N2. And make sure that this is, I'm doing it right. So V2 over V1, so the voltage ratio is equal to the turn ratios, and the current ratio is equal to the inverse of the turn ratio. With that, this actually is a result, or you can see that from this, if I multiply two sides by each other, you get V2 I2 divided by V1 I1 is equal to 1, which means V2 I2 is equal to V1 I1. V2 I2 is the power on one end, and this one is the power on the other end. And what this says is that the power on one end is equal to the power on the other end. In other words, what it's saying is that whatever power that goes into the system is going to be delivered out from the other end, which basically goes well with what we assume. We said there's a perfect coupling between these two, starting from the fact that we said the coupling coefficient is 1, and that means that all of the power that goes in is going to be coming out from the other side. This component is called a transformer with this assumption. And these equations are used in the case that we can approximate K, or coupling factor, to be 1, and that approximation is a lot of times is good enough. to be used for transformers. In other words, k equal to 1 is the situation for an ideal transformer, which is a good starting point in a lot of circuit analysis questions. So the discussion that we had ended up giving us basically a new component. This component called a transformer. And with the transformer, you can do something interesting if you notice. You can play with these number of turns and get into a situation where when you apply a voltage, you can actually kind of amplify that voltage on the other end. Now, you have to be careful with this because all of these assumptions that we're having here is only true if the voltage and currents that are applied in this situation are alternating voltages and currents. And we haven't started discussing that, and that's why we have to leave this discussion where it is and then come back to it and use them when we start understanding what I mean by alternating voltages and currents. To just quickly tell you what really stops us from using this for things that are the voltages and currents that are not alternating, let's consider the case that we have a constant current and a constant voltage. If you apply a constant current or a constant voltage here, you are going to get a magnetic field, but that magnetic field is a static magnetic field, and that magnetic field is going to go past through the other inductance. But the problem is that you would not get any voltage associated with a constant magnetic field, and that if you know anything about Maxwell equations, you know that the electromotive force really going to couple to magnetic field if that magnetic field is changing, right? So it's a derivative relationship. So if you have a constant magnetic field, you're not going to get any voltage as a result, and therefore there wouldn't be any current as a result. I'll leave that at that, and then we're going to go back and use these kind of equations once we know about alternating voltages and currents and how to deal with them, which is the number of next lectures that we're going to start basically going into from this point on. Thank you very much for your attention, and from this lecture on, we're going to switch our attention to alternating or sinusoidal voltages and currents and see how we can deal with circuit analysis or implement the circuit analysis algorithm when the kind of voltages and currents that we have are no longer constant voltages or currents. Thank you.